So I left the last part off on a little tease of how can we improve this, and this is where the minimally invasive biomarkers comes into play. So minimally invasive biomarkers and non-invasive biomarkers. Let's just do a comparison. So traditional invasive biomarkers, those comprise of, say, tumor biopsies, serial CT, MRI imaging, tissue-based molecular profiling, or radiographic tumor volumes. And the limitations of those can be that they are invasive, costly, burdensome, and we often get very sparse temporal sampling because of it. And oftentimes when we're doing like a simple biopsy or a single time point, we're only looking at a snapshot in time. We can't see how it evolves over time. So that can often lead to bias. Now, with minimally invasive biomarkers, those are blood-based biomarkers such as ctDNA or circulating tumor DNA, PSA in the case of prostate-specific antigen, or cell-free DNA. Other liquid biopsies I mentioned earlier could be urine or saliva or cerebrospinal fluid. And then, of course, we have patient-reported outcomes. Those are survey data, and then wearables. I think all of us, most people have like an Apple Watch on that can, we can actually collect patient data through those. Now, the benefits of those are they're dynamic, and we can get longitudinal information from them. It's low burden for the patient, low risk for them oftentimes, can be collected frequently, as I said, and they're often much more affordable than the alternative. So the minimally invasive, in this case, non-invasive biomarker that I want to focus on today is patient-reported outcomes. So those are, as I said, surveys. In our radiation oncology department at Moffitt, patients fill out a PRO survey at each visit. When they're sitting in the waiting room, they're asked, how are you feeling today? How did you sleep in the past week? What is your fatigue level? Are you eating? We're looking at all of these. Do you have a rash from the treatment? And this information, it provides insight into how the patients perceive their health and their treatment effects. And as I said, these are routinely collected at Moffitt, not only in our radiation oncology department, but in other departments. But that is the one that we do it as regularly as possible. These are distinct from typical toxicity measures reported by the clinician because it's coming directly from the patient. And this is an emerging field. It's emerging as an important metric in cancer precision and personalized medicine. Now, there have been multiple studies that have been looking at the value of PROs, specifically this one by Kerrigan et al., where they were looking at PROs as a prognostic biomarker. So they were looking at 4 different cancer types, in this case, non-small cell lung cancer, melanoma, colorectal cancer, and breast. And they looked at different domains or patient-reported symptoms. So looking at physical function, pain interference, fatigue, anxiety, and depression. And what they found from there was that different cancers have different profiles. So for instance, non-small cell lung cancer patients tend to have a lower physical function, but higher levels of fatigue. Right? You can see melanoma patients, they tended to do a bit better, where they had very low levels of anxiety and depression compared to other cancers such as breast or non-small cell lung cancer. Now, they looked a little bit deeper to see, can these symptoms actually inform overall survival and progression? And what they found here was that there was physical function actually served as an important, it was most strongly associated with overall survival and hospital-free survival. Just that one symptom alone, where they're looking at it for these different types of cancers. PROs have been used as predictive markers. This was a randomized trial where they were comparing. The patients could either enter their symptoms into like an app, or they would, and when the app would send a signal to the clinicians to say that this patient's symptoms are getting worse, and at that time that would prompt them to come in for a visit. They compared that versus just their standard monitoring, where they would come in every 6 weeks for standard scans. And so this is an example of a patient here. I'm sorry that the resolution is not the best, but this was their first, this was one scan, their first scan that they came in for. They had an objective response after their induction chemotherapy. They watched these different symptoms. So these are showing weight change, appetite loss, pain, cough, depression, fever, face swelling. And you can see the ones that are turning orange or are red in the middle. Those are the symptoms that are getting worse over time. And this is when they got as bad as they could get, I guess. It sent an alert through the system, And that is when they were encouraged to come in for a scan. And when they came in for the scan, this is where they actually saw that they had progression. Then they gave them a different type of treatment. They gave them docetaxel. Again, they watched them over time with their symptoms, where they're entering them every week or so into the system. Again, it sparks an alert in the system. They come in. You can see at this time the patient had progression. They're put onto nivolumab, and then they continue to monitor them over time. So this is the value of PROs, just allowing you to make decisions sooner rather than waiting until it's too late. There was also another study where they were, with this same study, this web-based study, they compared between the patients who were on the web-based monitoring versus the control group. And what they found was that the median overall survival was extended in the web-based monitoring group compared to the control group, where they extended it by about 9 months just by entering these symptoms into the system. And this was done. Now, these again are just looking at how they're changing over time. What we wanted to do was to see how they change over time in a different study. So this is a group of patient-reported outcomes, 20 different symptoms over those 85 patients that I mentioned earlier. And for this, the symptoms can range from not at all to very much. Each row here is an individual measurement, an individual time. If I zoom in, it's separated by these gray bars for the individual patients. So you can see that some patients had a lot of measures, some patients had very few, and some patients you can see that that intensity of the blue is increasing over time. Each row here is an individual symptom. So this is fatigue, shortness of breath, cough, and insomnia. But as I mentioned, we're looking at 27 different symptoms. And what we did with this was just to see, do these changes in these symptoms, do they correlate with tumor volume? So you can see for patient 33, for instance, their volume from one time point to the next, it increased. And we looked at their symptoms, and we found that insomnia was increasing, whereas shortness of breath, dizziness, and fatigue were decreasing. At their next time point, their volume continued to increase. Insomnia continued to increase. Shortness of breath did as well, fatigue, but dizziness stayed about the same. And then it's starting to come down now. Now insomnia is showing a similar trajectory. So we looked at them over all of our PROs for different patients, and we found that out of the 27 symptoms, insomnia was the only symptom shown to be significantly associated with changes in volume. So this is the minimally invasive biomarker that I was talking about earlier that we're going to be using to see if we can improve our predictions. Okay, so onto this data now. This is the same data set that I mentioned, 85 patients. We have on average 3 volume measurements, as I mentioned before. And these longitudinal PROs, these questionnaires were actually administered every 2 weeks. So it's a much larger data set, where on average we have about 12 surveys completed per patient. As I mentioned before, insomnia was the only one that significantly correlated with volume. So we actually conducted a study a couple of years ago where we tried to see, is insomnia by itself predictive? And what we found, this slide is a little bit busy, so I'll walk you through it a little bit, if this works. Yep, okay. So these were the different insomnia measurements on different days. So you can see that this one was about a month apart. They were told to complete them every 2 weeks, but some of them were a bit longer. So from one time point to the next, the insomnia level went from a 3 to a 2. And we were just looking at simple increases and decreases. So because this insomnia decreased, we're going to predict that the patient is going to continue to have stable disease. And when they actually come in for their scan on day 91, the patient does in fact have stable disease. And you can see that that pattern continued from day 0 all the way to day 88, where it just continued to decrease or stay about the same. Now on their next volume assessment, this isn't working the best, so I'm going to stay here. At their next volume assessment from day 88 to 101, their insomnia increased. And at that point, we predict progressive disease, and we were correct. Now, surprisingly, these are just simple increases and decreases. The model was able to correctly predict progression with about a 77% accuracy, on average 45 days prior to the next scan. So just simple
This is just based on insomnia, no other data?
Just insomnia, yep.
And these are the same 85 patients?
Yep.
And insomnia is just ask the question, so they just fill out how they can sleep, how they...
Exactly, yep.
So they were used like a watch where they measured...
Nope, it was just the patient reported insomnia levels, yep. Yeah, we were surprised that it was that predictive. We published this in Clinical Cancer Research a couple of years ago, so if you're interested, you can take a look at it. But what we wanted to do now was to see how can insomnia be systematically integrated into our TGI predictive pipeline to enhance model performance and clinical translation. And the issue with this one, even though it was highly predictive, this is just looking from one time point to the next. What we want to know is what's happening in between. We don't want to wait until the patient actually has progression. We want to be able to predict, like, you're likely to have progression within the next 2 weeks if you don't come in sooner, right? So that's what we're trying to improve on here.
Was insomnia correlated with other of these measures?
Yes, it was correlated with fatigue. There was another study that actually showed in a different data set that insomnia is closely correlated with fatigue, depression, and perceived stress. So they are correlated. Yep. Which makes sense. Fatigue and insomnia, like some nights I wake up, or some night in the middle of the night I wake up, I'm like, is this insomnia or is this fatigue? Fatigue is feeling tired during the day. Insomnia is having a hard time falling asleep or staying asleep. So obviously those two are going to be correlated with one another. Perceived stress, I was surprised to see that, and then depression. Yeah. All right.
It's true for me.
Were you saying you too, or did you have a question?
No. I have high correlations between those variables.
Yeah, for sure, right? So we modified our pipeline a little bit now. So initially, and I'll slow down a little bit here because I think there was a little bit of confusion on the last part. But we're fitting the model, and this leave one out, fitting the model over the volume data, and looking at the different lambda values. So this is what we're looking at, this cumulative probability. And what we did now was to separate them between patients who had an increase in their insomnia and a decrease in their insomnia. It felt like the right thing to do, right? Because it seemed to be so predictive. So those two distributions, they separated. And what we're going to do now is to sample from those distributions depending on the patient's specific insomnia level. So if it increased, we're going to sample from the red one, and if it decreased or stayed the same, we're going to sample from the black one. And again, we're going to make all these predictions, and we're going to, do ROC analysis, or, looking at our recall or precision to see how can we maximize our predictive potential. And then for the left out patient, we're going to take their initial volume, but also their changes in insomnia over time. And if they increase, we're going to sample from the red. If they decrease, we're going to sample from the black, and then make our predictions into the future, and then categorize them based on whether or not they are above or below the cutoff value that we're looking at. Okay. All right. So what that looks like for an individual patient is shown here. So this patient 128 is a continuous responder. Their insomnia levels looked like they stayed relatively constant at 0. We're looking at just the difference between these two time points that are shown in blue. They're staying the same. So when it comes to our cumulative probability functions, we're going to sample from the black one shown here. So we sample from that and then make our predictions. And here, the probability of resistance is very low. It's 2%. It's less than our cutoff. And because of that, we predict response. And I told you that the patient was a continuous responder, so that would be a true negative. All right? Now, for patient 120, this patient progressed after 2 months. You can see that their insomnia levels are increasing consistently over the first 2 months of therapy. And because it's increasing, we're sampling from this lower curve, the red curve. And when we sample from, where the lambda values are higher, but lower relative to each other. So we sample from the higher lambda values. Now our probability of progression is much higher than the other patient. It's 28%. Again, it's larger than our cutoff, so we're going to predict progression, and in that case, that would be a true positive. Right? So when we looked among all of our patients, our true positive rate increased. Before it was 75% for our early response. Now we're at 88%. Our true negative rate is higher as well. It's at 74%. So we can see that incorporating insomnia does increase our predictive potential. And what that looks like, I just have this graphic again among our 100 patients where we have this 10% prevalence in the early days of treatment. We have 10 patients who progress. Out of our 10 progressive patients, 9 of them would be correctly identified, 1 would be incorrectly predicted to respond. And then out of our 90 responders, about 24 would be unnecessarily escalated to additional scans, but 66 would be correctly predicted to respond. Okay. So we're doing better than we were before without insomnia. Now, when we look at the late response, it changes a little bit. And so with the late response, this patient's later insomnia level started to increase. I should have showed the trajectory before. It actually decreased, and then it started to increase. So when we sample, because it's increasing, we sample from the red curve. Our probability of resistance here is, again, very high, 28%. And this patient was actually a continuous responder, but we're predicting that they're going to progress. So that would be a false positive, okay? So among all of our patients now, the true positive rate is low, and our true negative rate is even lower, okay? It's at 39%. So, wow, I finished a lot earlier. I think I was anticipating questions. I was talking fast. So when we compare between the two of them, early response, we're doing a lot better. So what we're showing here is with and without insomnia. The bar on the left-hand side, the red is showing the number of true positives or progressive patients that are correctly predicted to progress. The black is showing those that were incorrectly predicted to respond, even though they progressed. And then these are our escalation. So this is in the early side. Before, without insomnia, our escalation was about 29%, or 29 out of the, in this case, 72, not 72, can't do the math right now. 70, I can't remember, whatever. Out of all of our responsive patients, we're saying that 29 of them are going to be escalated. And then when we add in our insomnia, that can reduce to 24. And up here, we are correctly predicting 1 more progressive patient when we are doing it in the early sense. And then in the late sense now, we're correctly predicting 13 out of 17 progressive patients without insomnia. And with insomnia, I think these actually are switched. This should actually be switched. With insomnia, we're doing 13 out of 17. Without insomnia, we're doing 11 out of 17.
So does it get better or worse?
It gets better, but not by a large margin.
Because now it shows that it
Yes,
gets worse.
I made these are wrong.
Okay.
It should be switched. I messed up on this slide. They should be switched. Long story less long is that insomnia can reduce unnecessary scans in the early stages of treatment, where we can look at those early changes, they're predictive of response. But later on into treatment, we have a harder time doing that. And one of the things that I think is the main issue, as I mentioned, as I alluded to earlier, is, say, for instance, this patient here, their insomnia actually decreased in the early stages and then increased. So they were doing well from, in their early time points where it was coming down, but then once it's increasing, this is probably due to toxicity from the treatment, and the model is not accounting for toxicity. We're just looking at straight volumes. Go ahead.
So this is a really stupid question.
No, it's not.
If I was one of those patients, I would call my PCP and say, give me some trazodone or prescribe me something. Do you have prescription information here?
I don't. No.
Because that could really mess up.
You're very correct.
I also have a question. So you account for insomnia in a certain way, but isn't there a standard way to do this through multiple regression type analysis?
Standard, I wouldn't say standard. We're now looking at...
It's a classification task, right? You want to put them into one of two classes, progressor and non-progressor. And you have these different types of data. And I think this is what's handled by multiple regression.
Yes. We're not looking at it in that sense. But yes, we could.
But that would be a standard, I think it's a standard way of doing it.
Yes. That would be like a standard statistical regression model. Yeah.
So what are the advantages of not doing multiple regression?
What are the advantages? I can't say. We try to keep things as simple as possible. We're now looking at Markov chain models instead, trying to follow the trajectories over time, the PRO trajectories, trying to come up with an overall symptom score from our Markov chain models, and then inserting them into this model instead to see if we can improve our predictions, because it could just be that insomnia is correlated with other PROs and maybe we should be considering those instead. So we're trying to expand upon this now, where we see in the early stages, yes, insomnia works, but later on, it's not doing as well. And another issue that we have is the timing between measurements. In the early stages, they're coming in for their scans every 6 weeks, standard, right? In the later portions of the disease, we have some patients who wait as much as 10 weeks, 12 weeks, 16 weeks for their next scan. And those are not messing up, but because we're predicting to the next time point, their probability of resistance is a lot higher than if they had came in at the standard 6 weeks. So that's also causing a lot of our false positives. So there's a lot of different factors that we have to consider here, but I just know early we're good, late not so much. Yes.
Let's catch us up a bit on this question. You were showing, like before, a classification that is only based on the insomnia thing. So the question is, how much better do you actually get by combining this? Or I think this is a bit on this regression task. You know, you could ask the question, how good are you just based on insomnia? Maybe one or two other measures.
Yeah.
Multimodal logistic regression.
We haven't done that comparison though.
These numbers before, but
Pardon?
we had these numbers before.
Yes, so we were doing, before that accuracy that I mentioned, that was combining both early and late, and that was a 77%. Now when we're looking at both of them, where we're looking at volume and insomnia, it's obviously reducing. I don't have the combined accuracy right here. Remember in the pipeline where I said that this is very problem specific, what we're maximizing and minimizing? What we actually found was that we shouldn't be focusing so much on the accuracy as we should be focusing on the true positive rate, because that's really what we're interested in, is correctly predicting progression. And that just focusing on accuracy alone takes an average of all of the patients together. And if we only have a 10% prevalence, it can skew the accuracy a little bit.
This is actually another question. I mean, basically, it's a threshold thing. So you kind of can move these false predictions around between the positives and the negatives. So you can probably move it to be more safe on the true positives.
Right. So with this, with the standard ROC analysis, you tend to try to get in the top left corner. So you're trying to have your true positive rate as high as possible, your false positive rate as low as possible. And if we do that, we actually get a worse prediction where we're looking at that. But if we set a threshold to say that we want our true positive rate to be at least 75%, for instance, then we can get but that results in a lot of false positives. So it's a trade-off between the two of them, right? What is the right metric? That's always the issue when it comes to prediction. So
False negatives are the worst, right?
False negatives are worse. That's what we consider it, right? Because we want to be able to predict progression. That's important. Yeah. Yes.
So, going back to the first talk.
Yeah.
Your model is basically just a linear differential equation, and all you're doing is keeping track of the call it the birth rate of the growth rate of the tumor. And so you do well at the beginning, and then when you try to model at a later stage, it isn't as good. And you said, well, it's probably due to toxicity. Have you tried to use that? I'm impressed that that simple model does so well. But have you tried to think about toxicity the same way that you're trying to deal with lambda, the lambda variable? That toxicity decreases the, I don't know how it's changing the growth rate, but just putting in an extra model like that and
Yes.
like that.
So that's where the Markov chain model is coming into play. So we're trying to, with that, we're getting an overall symptom burden. I don't have any slides on it yet because we haven't fully fleshed it out yet, but we're getting, we have an overall symptom burden where, what is the symptom burden for the patient, but then individual toxicities, so treatment-related toxicities or lifestyle-related toxicities. Do we need to model those separately, and do they have a different effect on the lambda value?
But they don't, as such, increase the growth rate, right? Toxicity is a side effect of the drug.
Right.
So it will not affect the tumor growth. It
If
may
you say
affect the dosage of the drug. So the patient may say, okay, this is awful, I'm not taking this drug. Is that how one would account the effect of toxicity, or?
Yes. Yes, you can say that
reduction of the dose.
that the different toxicities that we're measuring are going to have different effects. It might be on the growth rate, where if you have high toxicity, you're not taking treatment, you're likely going to have a higher
So
tumor
effectively,
growth rate.
it increases the growth rate.
Exactly. Yeah. Like I guess it's like an indirect effect of it, right? If you're not taking the treatment. So we're looking at the Markov chain models to see how we need to model those. We need to incorporate all of these different things that are at play.
So your colleague Joel Brown, right?
Pardon? Yes.
Your colleague Joel
Yes.
Brown just said this article on
Uh-huh.
how to use toxicity in adding to the mathematical model to use
did?
toxicity. Yep.
I didn't see it. I'll have to.
Kathleen and I are co-authors.
Okay. I need to look. So you should have said me. Why did you say Joel? You should have said you did it then.
No. He
I'll
was
look
the
it up
senior.
then.
He was the senior.
I will look at it.
Yeah.
Involved.
Ask Kathleen the questions.
All
I
right.
have a question.
Hey.
So I have filled out patient study, like these things, and like week to week, I can't remember how tired I was, how many times I woke up. Did I call it a 3 or 2, and then next week I have to call it a 4 or 3? Like, there's so much subjectiveness in this measure. Have you thought about, like, it seems very specific. You're like, oh, did it change by +1? And then that's seeming to be quite powerfully
Yeah.
predictive. But there's so much noise.
There is a lot of noise. I agree with you. And I think maybe that's why early on it's good, because maybe they're more conscious of it from the very beginning. But then you get fatigue over time. You're just like, I don't want to do this survey. I do that. You do a survey just for work, and you're like, okay, the first 4 pages I'm going to answer honestly. And then the next one's agree all, right? We all do it. So I agree that is something. When it comes to maybe being more precise, maybe we need to be looking at maybe wearables instead. So we do have another study in ovarian cancer where we're collecting PROs, but we're also collecting wearable data and looking at patient-specific circadian patterns instead of just relying on their PROs where they're reporting it, but you can get it directly from how are they sleeping, how are they feeling, because there is a lot of noise there. Yeah. I thought I saw one over here.
Yeah. So just, if I understand it well, so basically, even without insomnia, you just take the initial tumor size, right? And then now you use your lambda distribution to get these curves. But so for a given tumor size, you always get the same curves,
For a
right?
given tumor size, the same curve.
All these size curves, right?
Yeah,
These size curves, and so now you know the probability for each tumor size. So you could have like probably you have like here you have the initial tumor size, and then here you can put the probability of relapse, right? And so you can have another one where you have insomnia, and so
Like predicting insomnia going forward, is that what you mean?
no, I mean you would have another curve when for patients who have insomnia or patients who don't have insomnia, you just have 2 curves. So basically,
I think that's what
that's
they're
what you
doing.
do.
Yeah.
Okay.
So the first part was without insomnia, where we're just
Without
looking
insomnia.
right.
yeah.
So for each patient, like patient 102, we have it where we're not considering insomnia at all. We're just doing it
Yeah.
straight from the lambda, and then we have this one.
But basically, so all the differential equation, you just use it to get this lambda distribution, and after you have, it's only the initial tumor size which will predict and whether they have insomnia or not.
Exactly.
Okay.
All right. So I think I've pretty much gotten there. This is just the conclusions, but we kind of talked about it. And then there's the limitations, right? So the TGI model is most likely, just because of part 1, these are the final conclusions, is that the TGI model is likely not accounting for resistance mechanisms such as a suppression from the immune system. So maybe our model is too simple. TGI model is too simple. Now, insomnia symptoms gradually reduce after the first or within the first 5 months of treatment. The studies have shown that. And this is likely contributing to poorer predictions later into treatment because there is no insomnia, so we can't use it to make these predictions. So wrong model and potentially not enough of a signal. And then I often get this question, is it the insomnia that's worsening treatment or the poor treatment response is causing the insomnia? So we don't really know one way or another how that goes and how that affects the model. And then, so what we're doing right now is validating the early prediction response in a larger data set. We have over 500 non-small cell lung patients, and we're trying to validate that for the early response. And then, as I mentioned, we're investigating how Markov chain models might be used to inform these PRO dynamics and make subsequent predictions. So that is all. Same acknowledgement slide as before, and I'll take any additional questions.